All right, welcome to Econometrics number 1, lesson number 1, where we discuss the introduction to regression analysis. So we are going to be doing lesson number 1 and lesson number 2 today, which is pretty much based on regression analysis. I think I did mention on our introduction last week that most of what we are going to be doing is regression analysis. Here, when we talk of econometrics, it's going to be regression analysis. All right, but I think last week again, we started off with the definition of econometrics, where I said it comes from two words, economics and metrics, which means measurement. So this is basically about economic measurements. This is what we are dealing with. All right, so to explain what econometrics is, we look at its goal and the method and its methods and its uses, right? So its method and its uses. So the goal of econometrics is the estimation of economic relationships, right? We also spoke about this again last week, where we said we are going to be measuring on relationships between economic variables, right? And then the main method, again, like I said, is regression analysis, and we are going to be making use of actual data in this instance. All right. And then econometric models are mainly used for describing economic reality, hypothesis testing, and simulation and forecasting, right? So we're also going to see quite a lot of this through the course of this module. And just a reminder, this is a theory module, right? This is not. There isn't much calculations that we do here. It's very few calculations, and most of what we are doing is understanding, right? It's understanding the terms, the econometrics terms, the meanings of those words, the application of those words, not so the calculation, right? So it's got more to do with our interpretation of what we are saying. So in other words, if this was, say, statistics, will probably be on the part where you are interpreting the results, right? Interpreting the results, maybe. Yeah, basically that, more of your interpretation. Right, so econometrics generally makes use of these inputs here. Economic theory, of which you are most likely good at that, right? Economic theory, you've done that from first level right through. I think some modules, some third level modules still do have some economic theory, but most of it you do second level, most of what we make use of here. And economic data, right? And then of course, statistics, we need to have FM background of statistics. I think STA 1501 or 1502, one of those should be a prerequisite for this module anyway. All right, so let's talk about economic theory now. So in the previous modules, I think also last week we had a brief discussion on the demand curve. I think the law of demand, we were talking about the law of demand, the relationship between the price and the quantity demanded. I think I was stressing some points there. Then we can also talk about the consumption function. I think this from your ECS 2602, you will remember this, right? Where your C is equal to C bar plus CY there. Where I think if you remember well, C there was the autonomous consumption, right? Which was that part of consumption, which is a constant, right? And then of course there was that marginal propensity to consume. So what we're going to be doing here in econometrics is basically seeing how people end up coming up with these relationships, right? How you end up concluding that this is the relationship between consumption and income, right? Between private consumption in this instance and a person's income. So those relationships can generally be deduced through econometric models, right? Which is going to be mostly through regression analysis, what we are going to be doing through the course of this module, right? So We make use of regression analysis. Why? Because generally speaking, it enables us to calculate the slope coefficient. It also enables us to calculate the constant term. So what do I mean by those? If you remember from your basic math, a straight line was in the form of y is equal to mx plus c, where you can remember that m represented the gradient, which is the slope of that line, and then c represented the y-intercept. In other words, where that line was crossing the y-axis, so of which we are referring to that now as the constant. But one of the assumptions that you realize now when it comes to regression analysis, since we're making use of this when dealing with data, actual data, you hardly ever get a linear relationship, which is a straight line relationship between two economic variables, right? I think you are all familiar with how a scatter diagram looks like, where you've got lots and lots of dots there. Most of what happens in reality, you don't really get a straight relationship. For example, if you are going to be assessing, say, a person's spending against their income, right? Putting a person's spending, say, on the y-axis, trying to predict a person's spending on the y-axis, and then putting on the x-axis a person's income. I expect that when a person's income goes up, definitely their spending is also going to follow suit, right? But you realize that as you collect data, say, over the course of a year, you realize that there isn't really a straight line relationship between those variables. In other words, you are not going to increase a person's spending, say, by 10% and expect to get, sorry, you're not going to increase a person's income, say, by a consistent amount, and you expect person's spending to be increasing also by a consistent amount. It's not always the case. So you find that maybe the 1 month it increases by a certain amount, and then on the other month it increases by a different amount, etc. So at the end of the day, if you're going to be plotting that on the Cartesian plane, you're going to end up having a scatter diagram. So what regression analysis does, therefore, for the purpose of theory, it basically assumes a linear relationship between those two variables. So in other words, we foster a linear relationship between two variables. So which, if you remember well, this would be something like a line of best fit, right? I think, okay, we don't really, this is what it basically looks like here. So you've got different points there, which are represented by those dots there. So at the end of the day, you then draw a line that you feel that the line represents all the plots that you've put there on the Cartesian plane. Just a line that's going to be representative of all those points, and we call that the line of best fit, right? So you can basically draw that line, through observing those points, right? And then you can basically put a line where you think it fits in the middle, you can put that. But generally, regression analysis is the best estimator of that. It basically gives you the perfect line, right? It actually gives you the perfect line. So with any set of data, then you can apply regression analysis to come up with to come up with an equation, right, which is basically a straight line that's going to be representative of all those lines. So at the end of the day, if you're going to be looking at something in macroeconomics, like that consumption curve there, if you're going to be collecting data from states SA, you're going to be having quite a lot of dots, a lot of points there, then you can just use regression analysis to come up with a line that best represents, the data that you have there. So from that line, if you can come up with a line, that line basically comes through the making of that equation, or the formulation of that equation through regression analysis. So when you do that now, that equation is going to give you the intercept, the y-intercept. So in other words, which is the constant, which is that C bar there. right? Which is that C bar, which we say is the autonomous consumption. So which is the consumption before you even have any income, right? And then that little C, which is the marginal propensity to consume, there is going to be representative of the gradient of the slope of that line there, right? And then Y, of course, is Y in that regard there is the same as X, right? It's going to be the same as X. So you're going to find that Y. You should ideally find that Y on the X axis. So it's the explanatory variable, right? Which is the independent variable. So last week we were saying what you expect to find in the regression analysis is the dependent variable and the independent variable. So the dependent variable is the one which you are trying to predict, right? Number one is the one which you're trying to predict. And then number two, it is the effect, right? It is the effect. So in other words, it is the one that we expect that it's going to be affected by what happens to the other variable. So in this instance, if you have consumption there as your Y or as your dependent variable, then we are simply saying that your consumption is dependent on your income, right? So which is what you will see there, I believe, just on the notes there, just below. When we talk of causality, right? By that we mean in which direction is, in other words, in which direction is the effect going? So who's causing change, you know, and who's responding to change between those two variables? So that's got to do with the, of course, your understanding of economics and what you've read, your theory behind the, right, your theory base. That's got a lot to do with that. So what regression analysis basically does, it just tells you the relationship, the strength of that relationship. You can basically make conclusions based on that, but it will not tell you exactly if your consumption has increased because of your income or if your income increased because of your consumption. So it's not going to tell you. What's going to tell you that is the theory, right? So that's what we are seeing there. If you look at the sharp contrast between the monetarists and the post Keynesian economists there. So if you are going to look at this, for example, demand curve. So normally we argue that according to the theory, we know that a change in the price causes a change in quantity demanded, right? A negative change in the quantity demanded. But couldn't there be a case where a change in the quantity demanded affects the price? You see? So now it's a matter of in which direction is causality going, you see? So basically what regression analysis does, it gives you that formula, right? It gives you that formula, but it's not going to tell you that the change is as a result of the price or the change is as a result of the quantity. Just to give you an example, okay, we know the first part that definitely if you take the price up, we expect that the quantity demanded is going to go down. This one we know from our theory. But what happens now to a situation where, for instance, people boycott a product? What do you expect is going to happen to the price? See, so that in itself can drive the price down. You see, that can also drive the price down. So that's a different scenario now where you have causality moving in a different direction now. So as you are going to see now, as a statistician or an econometrics student, you can basically collect data and analyze the data, right? But obviously your analysis will have to be based on the theory. It will have to be in line with the theory at the end of the day. Your explanation, now fine, you can see what's going on. You've got the mathematical figures, but now the underlying theory behind what's happening there is also just as important, right? So remember, we use, as we said earlier, the goal of econometrics is to make estimates of economic relationships, and some places where that can be used is in making predictions, right? So when you're going to be making predictions, it's pretty much important for you to understand, therefore, the cause and the effect in terms of these variables, which one is initiating, or in other words, to put it simply, which one is the exponential variable? Because the exponential variable, which are the x variables, which are the independent variables, are the ones that are having an effect, supposedly having an effect on the y variable. So as you're going to see later, part of your job is to decide there which one is the y and which one is the x. All right, so I think the last part there will pretty much, econometrics cannot resolve the theoretical differences between two different schools of thought. This is what we are basically talking about here. Causality depends only on theory. So what we basically do, we come up with an equation, right, at the end of the day. But in any case, we need to base our equation on theory at the end of the day, right? So we cannot use that to resolve some conflicts between two different theories, okay? Because at the end of the day, I mean, the relationship is not going to be changed whether one can be y and the other can be x, but it's still going to remain the same at the end of the day. All right, so we also spoke about data types, right? Because we are going to be relying quite a lot on data, right, in doing our econometric models. So types of data, there are 3 types there which are listed for you: the time series, the cross-sectional, and then the panel data. So we touched on that again last week. So with the time series, we say the same variable is measured over time, right? So the change there is the time, right? We are measuring that there over a period of time. And then cross-sectional, then we are going to be looking at, say, if you're going to be looking at, let's say, the GDP within 1 year, the GDP of, I think I made an example and said the GDP of certain countries in 2018, for example. So that's cross-sectional data. So you're looking at this within one period, right? Within one period at a particular point in time. And then panel data, which is the much complicated of those, is a combination of those two, right? So I think the example again that I gave on the last session, we said that's going to be, say you're looking at the GDP of certain countries between 2010 and 2015. All right. And then I think the rest of that you can go through. And then, of course, we cannot stress any further the importance of statistics here, but we are still going to do that, I think, the next 2 or 3 sessions. We're going to be looking at statistics, but specifically what's going to be important for us here. So most of it is going to be on the normal distribution, hypothesis testing, and the t-test there. So that's just about what we're going to be doing there. All right, so let's look at the uses of econometrics, right, where this can be used. Right, econometric models, so we are mainly now talking about where we are going to be using, or where you can be using regression analysis in practice, these regression models in practice. Number 1, most central banks have large complex models for their national economies, right? But why do they need that in any case? Like our South African Reserve Bank, I think you know that we use, we are in charge of, South African Reserve Bank is in charge, let me put it that way, is in charge of formulating the monetary policy, right? So in other words, they basically take care of the interest rates, right? They decide what the interest rate is. So in most cases, they do that, right, in order to achieve a certain level of inflation, right? So now you can already see that there is a cause and effect relationship. Now there is a y and x relationship. So where we are saying the bank seeks to achieve a certain y, so in this case our y is going to be inflation. So what do? They try to achieve that by adjusting the interest rate. This is just an example, a simple example. So whenever you have the governor of the Reserve Bank, announcing a change in the interest rate. It was because, for the most part, I think the interest rate has been going up as of late. So it's just because they are of the belief that the inflation is too high and they are trying to take the inflation down. All right. So in other words, your X variable there is going to be your interest rate, right? Which is your exponential variable. So they vary the interest rate so that they can change Y, that Y variable, which is the inflation rate, right? So now you have your X and your Y relationship. So in order for you to basically decide by how many basis points you need to increase or decrease or increase your interest rate, then you must have some sort of relationship that you have, right? Whereby you can use it to predict the inflation, right? So in other words, you must have your model Y is equal to mx plus c. You know that if you change your X by a certain amount, then your Y is going to change roughly by a certain amount. So this is where econometrics comes in. So if you're going to be working therefore for the Reserve Bank, you'll probably have a lot of data at your disposal where the interest rates changed and then the corresponding inflation rate there, and then use that information there to come up with a regression model Y is equal in the form of Y is equal to mx plus c. So ours is normally going to be written as Y is equal to beta naught plus beta 1 x1, right? So of which your x1 is going to be your exponential variable there. So which means you can basically use that to make a prediction, right? An easier way, because you have that relationship. You are targeting your inflation. Say you want your inflation to be at 3.5%, then you can put your inflation at 3.5% and then see what interest rates can correspond with that. Then you vary the interest rate to that amount. And then number two, the Department of Finance. Again, you want to see, let's take, for example, the effect of taxation, right? The effect that taxation will have on people's consumption, right? So based on this here, on that consumption function, see, you know that your Y there represents your disposable income, right? So if you play around there with people's taxes, what effect will that have on their consumption? So you can basically try and make that prediction. Why are you doing that? Maybe you want to decide because your taxes are going to be falling within the ambit of your fiscal policy. So you want to decide on the most appropriate fiscal policy that can either boost the economy, or maybe you also want to tone down the economy, right? You could also do that. So we are basically trying to simulate effects of alternative policy options, right? So if you're going to be increasing your taxes, then whose taxes are you going to be increasing, right? And by how much? Are you going to be taxing the rich? What's the effect of that? So do rich people's consumption change because of taxes? So if it does, by what percentage do you expect that change to be? What about poor people? See, that's what you're gonna be doing there. All right. So you realize that maybe as a presidential candidate, for example, I was watching some years back the presidential debates there between, I think it was Donald Trump and who was the other lady? I forget her name. Hillary Clinton, yes. When they were talking about, there was a point when they were talking about taxes. Oh, no. It was, I think it was the one before Barack Obama, when he was talking about taxing the rich to take the money and make transfer payments to the poor people. So some of those there, you can't come up with such policies without having good economic advisors, right? And then in order for you to be a good advisor, then you must have these tools here to be able to make good predictions, right? You must be able to make good predictions there. Commercial banks as well can use econometric models to better understand how different economic sectors and industries may react to shocks in the economy, right? So you need to plan ahead, sometimes as commercial and civil as businesses. If you are quite a big business, then you can use these models to be able to plan ahead. You can be able to predict how your demand is gonna go, maybe by a change, as a result of a change in people's incomes. Just now we know that the government did not increase people's incomes, right? For the civil servants, they didn't get an increase now. So you can maybe estimate, if you're a business owner, estimate how the demand of your product is gonna go based on that. All right, so you are basically using that for forecasting and planning. All right, and then these here are examples where econometric models can be used, right? Structural analysis, where you are basically having numbers there, right? Where you've got a number there for your C bar and a number there for your little c for your marginal propensity to consume, right? Structural analysis there. So structural analysis basically means we are gaining quantitative knowledge about the relationships between economic variables. So these are not always the same. They probably change over time, etc. Okay, and then of course, policy evaluations, right? How good a policy has done, you can be able to assess that there. Easy, you can basically get the data for that. And then forecasting, you can be able to make predictions based on that. All right, but what then is regression analysis? Assume that you have two data sets, a series of private consumption expenditure, that one, and a series of gross domestic product, say for the period of 1980 to 2020. And then you believe that there is a macro relationship between that consumption expenditure and GDP, specified as follows. That's there, where A and B are the coefficients of the equation. So regression analysis is simply a technique to estimate the coefficients of that equation from the data. So regression analysis, you basically take data, like what we've been describing now. You take your consumption between that particular year, we say June 1980 and 2020, then you take the corresponding GDPs between those years again, 1980 and 2020, and then you use that to come up with your A and your B, right? Which are your coefficients. So once you've done that, your A and B, once you have numbers for your A and B, it simply means that you have an equation, and you can basically use that equation for forecasting, policy evaluation, structural analysis, any of those there. How are you going to be forecasting? Because you can already see now in forecasting that you know that every time consumption went up by a certain amount, your GDP is expected to increase by a certain amount. Given there, I think we're going to learn later how to interpret this, given that equation there, and then you are able to forecast in the future that, okay, at the rate at which this consumption is growing, then you can expect that the GDP is going to move in that direction. In what direction? All right, and then what's going to be important for examination and assignment purposes is the difference between the estimated regression equation and the true regression equation. So this is going to be there here again, you know, the notes that I'm going to make. But most importantly, a true regression equation is basically based on the population. So it represents the true relationship between economic variables. So that's difference number one. It's going to be based on actual population, right? So in other words, if you're going to draw a true consumption line of the people of South Africa, then you must have interviewed each and every person or collected data from each and every person here in South Africa. Then that's going to give you a true relationship between people's consumption and their incomes, right? So it's based on the actual population. Whereas an estimated which is what we normally do estimates. It's an estimate because it's going to be based on the same. So the true regression line, difference number 2, the true regression line again can never be observed. Right? You can never draw a true regression line because there's never a point in which you will ever collect data from the population, right? From the whole population. Why is that the case? You can never do that, right? In any case, it's imprudent to do that, and you are bound to make a lot of mistakes. So we normally deal with estimates based on samples, right? Based on samples. So the difference number 2 is it can never be observed, right? It can never be observed. Whereas the estimated regression line can be estimated. All right. So why can the estimated be drawn? It's because now you have a sample, right? You have collected data. Then you use that data. That data is always the sample. It's not the whole population, right? It's always a sample. And then you take that data and then you come up with your estimates of your beta coefficients, right? Which are, in that instance, it's your A and B coefficients. But as you can see there on that diagram, there's those betas there. That one that looks like a B, right? So they are parameters, those coefficients, we call them parameters, we refer to them as parameters. So those estimated parameters are going to be based on the sample. That's difference number 2. And then difference number 3, if you're going to be dealing with the true regression line, then you're going to have what we call, right, there are 2 terms here that we're going to deal with, which are also Greek letters, which I'm going to introduce now. There's the error term, and then there's the residual errors, right? Which is the residual errors, right? So from the true regression line, you come up with what we call the error term, which is that epsilon, which looks like an E there, right? And then from the estimated, you come up with that little E there, right? You can see, let me blow it up there, that little E there. So the little E is called the residual error. And then this one here, stochastic error, which is the error term is referred to. So it is normally denoted as that epsilon, that Greek letter there. All right. So for examination purposes again now, the error term and the residual error, the stochastic error term and the residual error term basically differentiates. You are able to see whether you are dealing with a true regression line or you are dealing with the estimated regression line. So like we said, the residual error term is for the estimated equation, and the stochastic error is going to be for the true regression equation there. But over and above that, we need to understand now the difference between those 2 terms there. That's also another favorite of the examiners, the difference between the error term and the residual error. So difference number 1, of course, is that the stochastic error comes from the true regression line, whereas the residual error comes from the estimated. And then one cannot be observed again, that error term, because the true regression line cannot be observed, but the residual error can be observed. Right? You can calculate that. Okay. But you are going to get a lot of that there on the notes. So what you also need to know now is some of the sources of the error term and what the error term is, for starters. So the error term arises from as a result of our imperfect knowledge, or maybe sometimes there could be problems with the sometimes we're dealing with the sources of error term. So the error term is the difference between, right? It's going to be the difference between what you have on the line, or the predictions according to the line, So remember that your straight line there represents points on a graph, right? They represent points on a graph or points that lie on that equation. So the difference between those points now and the different observed points, which are those dots there, which is coming from the actual data, that difference there is the error term, right? Where we are saying your regression equation estimates that at this point, when x is a certain value, y is going to be another value. But when you look at the data points to a different plot altogether. It plots a different point altogether. So that difference between what the data gives you and what's on the regression line is the error there, right? It's the error there, which is the difference. So I think we're gonna see, if you look at the, let me just blow this up, where you see your E with your subscript 6 there. So that difference between what's on the line there and then what's on the point. So in this instance now, if you're going to be looking at the difference between that dotted line there, that dotted line there represents the, all right, this dotted line there represents the estimated line. Yes, that dotted line is the estimated regression equation. So that difference there is the residual error, right, which is written as E subscript 6 is the residual error. So which is the difference between the estimated line and the actual point. And then now the difference between the true line and the actual point is going to give you that stochastic error, which cannot be observed by the way. Remember I said the true line cannot be drawn, right? It cannot be drawn because there's never a point in which you can test the whole population. So it's just in our thoughts, right? So that difference there is going to be the stochastic error. So the one that we are going to be dealing with quite a lot is that residual error there. The difference between your estimation and what the data gives you is the error. So we are saying that arises because sometimes you can't really predict a person's behavior, right? You can't really know about a person's behavior. So at the end of the day, you can make a prediction that person A spending is going to jump by such and such an amount when you increase their income by such and such an amount. But when you check the actual data, then there's a slight difference there. So that slight difference could be caused by a number of factors, including the fact that people are, I'm looking for the words now, where, people have got erratic behaviors. I think we can safely throw in that word there. All right, so just go and have a look at that example there of that regression line. I think this is in the textbook. That's in the textbook. So you can basically use that to make predictions, right? Then on the last part now, before we conclude the session, I'm just gonna rush through lesson number 2, because it's a lot shorter than this. So now that we spoke about that regression equation there, how do you then come up with that regression equation? Then you use the ordinary list of squares, right? Use the ordinary list of squares. So what does this method do? It basically gives you the estimate of your parameters. So your parameters were your A and your B. Your parameters are your intercepts, right? Your parameters there is going to be your beta coefficients. So in other words, you find your beta coefficients using the ordinary list of squares, right? We will see later some of the reasons why we use this method, right? We are going to see much later. So what we're dealing with there now is a simple regression model where you've got y is equal to beta naught plus x1 plus beta 1. So in other words, where you only have one explanatory variable. So now we can introduce a situation. So there's a single independent variable in the one that I'm talking about, right? But there are situations now where y is not just affected by one variable, but there are many other variables that affect one. If you take, for example, your GDP is not just influenced by a person's or people's consumption, right? It can also be influenced by a host of other things like interest rates, etc., right? All those things have got an effect on a person's GDP. Even your demand of the product, right, is not just going to be influenced by the price of the product, but it's also going to be influenced, say, the price of related goods, right? And it's also going to be influenced by a person's preferences, it's going to be influenced by a person's income. So all those influences there represent, basically represent independent variables, which are explanatory variables. So which are your X variables, which are the ones that we can use to predict your Y. So if your Y is your quantity demanded of a certain product, then your quantity demanded can be affected by your income, can be affected by the price of the good we are dealing with, can be affected by the price of related goods also. And again, in related goods, you can have substitutes, you can have complements also. So it's a lot of things. So this is what reality is, right? So the good news is now you can come up with a regression model, which we can't exactly plot now on the Cartesian plane, right? But you can basically come up with a regression model that can give you the relationship between all those. So later we're going to be learning how to interpret those there. So just have a look at that example there, that activity 2.1. It can pretty much give you an idea of a multivariate regression model. All right, so we are basically gonna, I think, as soon as we can, we are going to run a regression model on Excel. We're going to run a regression model. Part of what's in the assignment there has got to do with running a regression model on a spreadsheet there. So we're going to learn how to do that there. And then more importantly, we're going to learn how to interpret that there. All right, so every time now you do a regression model, you need to ask yourself these 8 questions here. So we are going to keep coming back to this, but I'm just going to rush through them now. So is the equation supported by sound theory? So in other words, the background economic theory, is it sound? Does it make sense, right? So in other words, the fact that variables are moving in the same direction doesn't mean that they are affecting each other, right? For example, I think I once gave an example that I saw in one economics textbook that if every morning there are birds that, right, if every morning there are birds that sing before the sun rises, we can't conclude that birds are causing the sun to rise. You see? So in other words, if you can run a regression model for the birds singing and the sun rising, it's going to be positive. It's going to represent a strong relationship between those two variables there, but you can't then come up with a conclusion that the birds are causing the sun to rise, you see. So in other words, you need to have sound theory behind whatever you do. And then how well does the estimated regression fit the data? We are going to see that just now. And then is the data set reasonably large and accurate? You see, large and accurate. So if you're collecting data, make sure it's as large as possible so that it can, it can be representative of the whole population. You can't test 2 people and then draw a conclusion about, about 1,000 people. And then again, is ordinary list of squares the best estimator to be used in this equation? So later we'll look at other circumstances where it's not ideal to use ordinary list of squares. You can use other methods to come up with an equation, right? Which include maybe the general least squares, etc. And then how well do the estimated coefficients correspond to the expectations developed by the researcher? For example, you expect that your demand should have a negative relationship with your price, right? So what happens when you test something, you run a regression, and then it shows that there is a positive relationship? So you ask yourself that question now. But again, you remember that there are certain products that respond in that direction. But at the end of the day, when doing regression analysis, you have your expectations there. Then are all obviously important variables included in the equations? So are all things that affect the demand of the quantity demanded of the product included in that equation? You see, has the most theoretically logical functional form been used? So the functional form that we are using here in our OLS is a linear relationship. We are looking at a linear relationship, but some situations do not need a linear relationship or can't work on a linear relationship. Sometimes there are exponential relationships. So is a linear relationship the best? See, we are looking at that then. And then does the regression appear to be free from major econometric problems? So this we are gonna look at in future. These are part of the topics that we are gonna be covering anyway. And then most importantly now, we are almost concluding, most importantly, the overall fit of the estimated regression model. So this is your R squared, right? This is your R squared. So your R squared, you normally get questions on this, which is the fitness, the goodness fit measurement there. It's normally given there as your R squared. So here now, I think from statistics, you probably did your R squared. Like it measures how well your data set fits into your, how well your data set fits into the model, right? So in other words, how tight or how tightly close are your points, right, or are your plots to the regression line, right? So in other words, it basically measures your error terms, right? Basically measures your error terms. For example, if your R squared is small, right? If your R squared is small, it basically means that you can't really rely on your model for estimations. Why? Because your data set is spread across, right? It's spread all over the Cartesian plane. So fine, you have a line, you have a line of best fit, but your line is such that some of the points are lying far from the line, right? Some of the points are lying far from the line. So it means that there's a likelihood that your residual errors are going to be large at some points, right? So this is what we do. You basically, so in order for you to check the goodness fit there, you basically do that by doing the R squared, right? So it has a formula. I think we are going to see the formula much later, but there is R squared and adjusted R squared. So your R squared you normally use if you're going to be dealing with one independent variable. But as you start increasing your independent variables, where you have your x1, x2, x3, so in other words, so you've got many other things that affect your dependent variable, which is your y. Then under those circumstances, you need to use your adjusted R squared there, your adjusted R squared. So we are going to do more of these from our next session, right? So a major exam question that you get here, of course, is your difference between your R squared and your adjusted R squared. What do we mean by adjusted R squared? What have we adjusted the R squared to? That's what we are talking about there. And then the other thing again is this one here, the example of your misuse of your adjusted R squared. So in other words, also start off with circumstances under which using, okay, what happens, I'm not going to talk much on this because we are going to do it again. So, but what happens to your R squared when you keep increasing your X variables, right? Your independent variables, what happens to your R squared? And then what happens to your adjusted R squared when you keep increasing also your independent variables? So that one we are going to be looking at from the next session. All right, so other than that, I think just go through these notes and during the week, but not tomorrow or not the day after. I'm gonna do my own version of the notes. I'm gonna put in what I think is gonna be important. But it's gonna be much based on the textbook. Right? I'm gonna be extracting stuff from the textbook and adding probably just a few more things. Right. I don't know if we have any questions before we conclude the session.